Hello, welcome to day 3 of chemistry. Today we're going to talk about changes of state. After we get through this slideshow, you'll do some research of your own. Actually, you'll read an article and research a little bit about one of the changes of state and some applications for it. But today we're just going to jump right in. I'll do my best to go through this quickly so the video is not crazy long. But let's think about what we talked about yesterday, I believe. Outline the steps required in recrystallization. So I want you to think about recrystallization, that technique that we learned yesterday. And real quick, I want you to maybe write down the steps that you can remember in your notebook for recrystallization. So take a second, maybe pause the video and write them down. So the steps for recrystallization are: we need to add a minimum amount of hot solvent, right? That's maybe it's hot water, some sort of hot liquid that's going to dissolve the impurities easily, but enough that what we want, the desired product, is just barely dissolved, right? This gives us a hot saturated solution. As it cools, our solution of the desired product will decrease, and so it will come out, it'll crystallize, and then we can filter the crystals and collect them, and then we dry to constant mass, right? So those are our steps for recrystallization. This is a new question. How many changes of state can you name? You might also call these like phase changes between the phases of matter. So take a second, write down as many as you can, pause the video, and I will give you a moment. So, you probably got some of these. Some of these you might be a little less familiar with, but there is melting, freezing, sometimes called solidification, vaporization, evaporation, boiling. Those all kind of go together. Condensation, sublimation, and deposition. Those are the ones that we're going to talk about today. So, with those in mind, I would like you to quickly try and label this diagram. All right, so we have our 3 phases of matter: solid, liquid, and gas. And then we have all these different points. So like A would be changing from a solid to a liquid, B would be going in the opposite direction, E would be changing straight from a solid to a gas. So what is that called? See if you can name all of these changes of state. So I'll give you a second, pause the video, give it a try. So, solid to liquid, that is melting. A is melting. Liquid to solid is freezing, sometimes called solidification. Liquid to gas is vaporization, which could be evaporation or boiling, depending on the conditions, right? Gas to liquid is condensation. These two are the weird ones, right? Solid straight to gas is called sublimation. So when you have a solid and it skips the liquid phase, becomes a gas, it's called sublimation. And then going from a gas straight to a solid is called deposition. Sometimes people also call this sublimation, but we're going to call it deposition. We can also cause these changes if we imagine like the heat increasing from left to right, right? As you add more heat, you change from a solid to a liquid to a gas, or we can manipulate the pressure, right? So if we're increasing the pressure on something, it will start to compact, right? And become a solid eventually. As we write these in chemical equations moving forward, because we're going to be writing lots of chemical equations like this, it's important that we label what we have. So we have our state of matter over here, and then we have some symbols that I'd like you to learn. And then here's some examples. So like if we have solid iron in a chemical equation, we would write the elemental symbol for iron, Fe, and then in parentheses next to it, we would write an S for solid. If we had liquid bromine, right, we write our Br, and elemental bromine has two of them, so we have this two here. They are bonded together, and then we'd write an L in parentheses. We had oxygen, gaseous oxygen, we write a G, and then this aqueous one, it's a special thing, and it basically means that it is dissolved in water. Because we use water so often as a solvent, we dissolve things so often in it, we gave it its own special symbol. So this means that this is sulfuric acid, and that would mean that we dissolved the sulfuric acid into water. It's in an aqueous solution, in a water solution. So if we're looking at chemical reactions down here, like you might write, where we have solid sodium reacting with water to give us sodium hydroxide and hydrogen gas, we just want to make sure that we have those symbols telling us that this solid, this is a liquid, this is dissolved, right? It's aqueous, and this is a gas. And this is important because as we start to do experiments, we need to know what our products are going to be. And especially if we're going to get something like harmful, is it a gas? In which case we would need to do that experiment in a special location where we can filter out that gas, right? Here's some more examples. As we get into writing more and more equations, right, we might start to see this little symbol, which means that the reaction can happen in both directions. And this is just like melting solid to liquid, right? You know all these. This is just represented with the symbols now. So, because temperature affects the state or the phase of matter, we're going to look at some temperature graphs and see how they can describe these changes, right? So the graphs are really just a way to represent the reality of the things that are happening. So on this graph, we have the average kinetic energy of the particles in a substance, and then on the bottom we have temperature. So this is in joules, this is an energy unit, and this is temperature. This is Kelvin, which is a temperature unit. So my question to you is, what is temperature? You probably have an intuitive understanding of this. I want you to try and define it. So take a second, maybe pause the video, write down the definition for temperature, and then I will talk about it. So in chemistry and in science, we define temperature as a measure of the average kinetic energy of the particles. So a measurement of the average kinetic energy of the particles. Kinetic energy is moving energy, right? And let's just take like a gas, for example. A gas is moving around the room. Each particle is moving at its own speed. And as the gas gets hotter, those particles will move faster, right? So the average kinetic energy is telling us about the temperature. When you experience like a really hot day, all of the gas around you has more kinetic energy than on a day where it's cold, then it would have less kinetic energy. And the relationship is directly proportional as long as the units of temperature are Kelvin. So Kelvin is our special temperature scale, and it's special because it has a 0 point, which means like no motion. So 0 Kelvin would mean that the particles have 0 kinetic energy. And things don't actually do that in real life, but it is like this theoretical boundary that you can reach. So it's a special temperature scale that we're going to use in chemistry. 1 degree Kelvin is the same amount of temperature as 1 degree Celsius. It just has a different starting point. So the conversion is actually really easy. And kinetic energy is related to both the mass of the particle and the velocity. And velocity is like the speed, right? So how big it is and how fast it's going. And here is the equation to calculate kinetic energy. It's 1/2 the mass, right, times the velocity squared. So you can see it's related to both of these things. So I want you now to draw a graph. How would this graph be different to the previous one? And this, oh, sorry, not drawing, you're just comparing. This is a graph of the average kinetic energy of particles in a substance in joules and the temperature. Seems very similar, but if I go back, right, this graph is in Kelvin, and this graph is in degrees Celsius. So I just talked a little bit about how they're different. Maybe take a second and pause. Write down how you think these graphs would differ from each other. So on the last graph, we said we'd get a linear relationship, right? Directly proportional. We'd have this nice straight line going up. We would also have that here, but because 0 degrees Celsius is the freezing point of water and not absolute zero, our line would not start here, right? The absolute zero for Celsius is negative 273 about. So it would not be starting here, it would start somewhere else, right? But then our line would travel in a similar parallel upwards proportional fashion.